Okay, so this is the last video narrated by me, Jason Harlow. I'm finishing up chapter 3 on two-dimensional kinematics, and today's video is about relative velocity. So let's start by looking at this figure. We have Alex, who is standing still on the ground. We have Michelle, who's on her bicycle riding towards the right at plus 5 meters per second. And we have this red car, which is traveling towards the right at 20 meters per second. All of these velocities are relative to the ground. And we've defined positive being towards the right. That's sort of a historical tradition. The tree is not moving relative to the ground. I've just put this here, but what we sometimes don't think about is all these velocities are relative to something, to the tree, to the rest of the earth. So, relative to Alex, Michelle is moving at 5 meters per second. And I want to use the notation that using these subscripts, MA, where MA means Michelle relative to Alex. So V sub MA equals plus 5 meters per second. It means that Michelle is moving at plus 5 meters per second relative to Alex. VCA means the velocity of the car relative to Alex is plus 20 meters per second. And I guess VTA would mean the velocity of the tree relative to Alex. It's way over here, but it's not moving, so VTA equals 0. So that's the world according to Alex. If we look at the world according to Michelle, Michelle is at rest in her own reference frame, in her world. And if she's catching up to the car, but the car is going faster than her, the car is moving to the right plus, but slower by her speed of 5 meters per second. So 20 minus 5 is 15. That's the velocity of the car relative to Michelle. Alex over here is actually moving backwards relative to Michelle. He has a negative velocity. VAM equals negative 5 meters per second. And in fact, even the tree has a velocity relative to Michelle to the left of 5 meters per second. The whole rest of the world is moving along to the left at 5 meters per second relative to Michelle. So in physics, all velocities are relative to some observer. So let's give it a try here. You're running towards the right at 5 meters per second toward an elevator that is moving up at 2 meters per second. So relative to you, the direction and magnitude of the elevator's velocity are A, down and to the right, less than 2 meters per second, B, up and to the left, less than 2 meters per second, C, up and to the left, more than 2 meters per second, D, up and to the right, less than 2 meters per second, or E, up and to the right, more than 2 meters per second. Please pause the video, think about this, and then resume. Okay, so hopefully you got C. So the idea here is that relative to you, the whole world picks up this velocity to the left of 5 meters per second. So the ground is moving to the left at 5 meters per second. So something that was already moving, you now have to add the vector of the velocity of that object relative to the Earth plus this negative 5 meters per second. So there was 2 meters per second up plus 5 meters per second to the left is going to be something that's more than 2 meters per second, and it's going to be up and to the left. Okay, let's look at this nomenclature a little bit more. So here we have a train, one of these fast trains, and it's moving towards the right at 30 meters per second. Okay, so that is the velocity of the train relative to the ground is plus 30 meters per second. Now I want you to imagine, you can't see him here, but there's a passenger walking toward the front of the train at 4 meters per second. So what does that mean? I would call that VPT. The velocity of the passenger relative to the train is the plus 4. So if you wanted to know the velocity of the passenger relative to the ground, you would add these, and you'd get 34 meters per second. So notice that there's sort of a cancellation here if you use this notation. So velocity of passenger relative to the ground is passenger relative to the train plus train relative to the ground. So these inner subscripts are the same. They're both T's, so they kind of cancel out. And then the other thing to note is that the velocity of, if the train is going towards the right, plus 30 meters per second relative to the ground, then the ground is going to the left at 30 meters per second relative to the train. So anything 1 relative to 2, velocity of 1 relative to 2 will be the negative of the velocity of 2 relative to 1. So let's do an example here from the book. You've got a boat which is heading north toward across a river, and the river is flowing east. And the question is, what's the velocity of the boat relative to the shore? So the way we look at this is we say the velocity of the boat relative to the water is this 0.75 meters per second north. That's, I guess, when the engine is going on, the boat is pointing towards the north, and that's its velocity, what it would be relative to the still water. And then the velocity of the water relative to the shore is that the whole river is going 1.2 meters per second towards the east. And so the equation looks like this. Velocity of boat relative to shore equals boat relative to water plus water relative to shore. So these inner subscripts cancel out. And then you've just got a triangle here. It happens to be right angle triangle. There's your theta. You can use Pythagoras. Velocity of the boat relative to the shore is the square root of these two velocities squared, some of them squared. You get 1.42 meters per second. And then to find this theta, you use tan to the minus 1 of this opposite divided by the adjacent, and you get 32 degrees. So in the end, you would say the velocity of the boat relative to the shore is 1.42 meters per second, 32 degrees north of east. So let's give it another try. You are on an eastbound subway train going at 20 meters per second, but you look out the window and you notice a westbound train on the other track. And you know that relative to the ground, the westbound train is also moving at 20 meters per second. So what is the velocity of the westbound train measured by you? So is it 40 meters per second west, 20 meters per second west, 0, 20 meters per second east, or 40 meters per second east? So think about this, pause the video, and then resume. Okay. Hopefully you got 40 meters per second west. The way that would work is you could say you're in an eastbound train going 20 meters per second, so the velocity of u, the e, relative to the ground is plus 20 meters per second if you define positive velocity towards the east. And then the westbound train is also 20, but now it's going in the opposite direction, so v of the westbound train relative to the ground is negative 20. And then your equation looks like this. You want to know the velocity of the westbound train relative to u on the eastbound train. So it's v sub we. So that's going to be wg plus ge. I've arranged this so that the inner g's cancel. But we don't know velocity of the ground relative to the eastbound train, so we're going to reverse this by changing it to negative. So we're going to subtract v of eg. So now we know these. Velocity of the westbound train relative to the ground is negative 20. Then you subtract off the plus 20, and you get negative 40. So this is called classical relativity, when these velocities add linearly like this. So say you've got an observer on a ship that's moving towards the right, and he drops his binoculars. So if you ignore air resistance, what happens is these binoculars drop straight down relative to that person on the ship, and they hit the floor at directly below him. But since the ship is moving, if you're standing over here on the shore, there's now this horizontal velocity of the whole boat, and that is also added to the velocity of the binoculars. So the binoculars have a horizontal and a vertical component. But since they're separate, you see this parabolic path. The binoculars take a curved path. But what's interesting is that they both strike the bottom of the boat at the base of the mast, since the mast is going with the same horizontal velocity. So it works out. Either observer will see this same projectile, but it looks curved in one frame of reference and it looks straight in the other frame of reference. So that's it, and good luck in your physics course.